In the last episode, glycolysis broke sugar down into pyruvate, but over 90% of the energy was still locked inside it. Now that energy gets collected, this is the citric acid cycle, also called the Krebs cycle, the central hub of your metabolism. And here's the thing to hold on to from the start. The goal of this cycle is not to make ATP. It barely makes any. Its real job is to strip high-energy electrons off your fuel and load them onto carriers for the stage that comes after. And it isn't just sugar that ends up here. Carbohydrates, fats, and proteins, whatever you eat, are all broken down along different paths that eventually converge on the same small molecule, acetyl-CoA, a 2-carbon fragment. That's why this is called the final common pathway. No matter what the fuel started as, this is where it all comes together to be taken apart. But first, where does this happen? Not in the cytoplasm, where glycolysis ran. To reach the cycle, pyruvate crosses into the mitochondrion, through its outer and inner membranes, into the innermost space, the matrix. This is a watery, protein-rich environment, and the enzymes that run the cycle are concentrated right here, floating in the matrix, ready to work. The setting matters. Everything from here on happens inside the mitochondria. Before pyruvate can enter the cycle, it has to be prepared. And this gateway step is easy to overlook, but it counts. It's called the link reaction. First, pyruvate enters the enzyme complex. Then one of its carbons is stripped off and released as carbon dioxide. As that happens, electrons are pulled away and loaded onto NAD+, forming the very first NADH of this whole process. And what's left? A 2-carbon fragment is joined to a carrier to become acetyl-CoA. This step is irreversible. Once it happens, there's no going back. Now we're ready to enter the cycle itself. Here's the whole cycle, and the reason it's drawn as a loop. Acetyl-CoA, 2 carbons, joins with a 4-carbon molecule called oxaloacetate, forming the 6-carbon citrate. As the molecule travels around the ring, it's taken apart, step by step. Carbons leave as carbon dioxide, electrons get stripped off onto carriers, and by the end, oxaloacetate is rebuilt, ready to accept the next acetyl-CoA. That's the key. Oxaloacetate isn't used up. It's regenerated every single turn, which is exactly why the cycle can keep spinning. Let's walk through it. Phase 1 is setup. In the first reaction, the enzyme citrate synthase joins acetyl-CoA to oxaloacetate, forming citrate, the 6-carbon molecule at the top of the cycle. This is a strongly favorable reaction. It pulls the whole cycle forward. Then a second enzyme, aconitase, quietly rearranges citrate, the same atoms, just reshaped, to expose the right spot for what comes next. No electrons harvested yet. This phase is just getting the molecule ready. Phase 2 is where the real collecting begins, and it happens twice, back to back. First, the enzyme isocitrate dehydrogenase performs an oxidative decarboxylation. 1 carbon leaves as carbon dioxide, and electrons are stripped off to form NADH. The molecule drops from 6 carbons to 5. Then, immediately, a second oxidation does it again. Another carbon leaves as carbon dioxide. Another NADH is formed, and what's left is a 4-carbon molecule attached to a carrier called succinyl-CoA. 2 carbons gone, 2 NADH collected. The main disassembly of the carbon skeleton is now complete. Phase 3 is the one moment the cycle makes a bit of direct energy itself. As succinyl-CoA is converted into succinate, the energy released is captured directly. Building one molecule of GTP, which is essentially an ATP. This is the same kind of direct, hands-on energy transfer we saw in glycolysis. But notice how small it is, just one per turn. The cycle's real value was never here. It's in the electron carriers. So let's total up one turn. 2 carbons left as carbon dioxide. 1 GTP was made. And the real prize, 3 NADH and 1 FADH2, loaded electron carriers. And remember, because glycolysis made 2 pyruvates from every glucose, this whole cycle turns twice per glucose, so you double all of that. The cycle also regulates itself. When energy is scarce, high calcium, high ADP, it speeds up. When energy is plentiful, lots of ATP and NADH already around, it gently slows down. But here's the honest catch. After all of this, we still have almost no usable ATP, just a pile of loaded electron carriers, and they only pay off in the next stage, which is the one that finally needs oxygen. How those electrons become real energy, that's the electron transport chain, the next and final episode. Phase 4 closes the loop. First, succinate dehydrogenase strips electrons off succinate to form fumarate, but this time the electrons are loaded onto a different carrier, FAD, forming FADH2. Then the enzyme fumarase adds a molecule of water. And finally, malate dehydrogenase performs one last oxidation, forming the third and final NADH of the turn and regenerating oxaloacetate. The 4-carbon acceptor is perfectly rebuilt, standing ready to catch the next acetyl CoA. The loop is closed.